deep into the fuel panel, I'd like to make a schematic diagram showing the relationship between this fuel panel here and the fuel dump panel right here and how they're connected together. I have here on the blackboard a diagram of the lower portion of the fuel panel showing fuel gauge number 1, number 2, number 3, number 4, cross feeds 1, 2, 3, 4, center fuel tank, and the center fuel tank jettison overrides. Now, the relationship between the fuel crossfeed system and the fuel jettison manifold are as such. Imagine here, this is the fuel jettison manifold. It is completely independent and separate of the fuel crossfeed system. However, the two can be connected together. Now, at the end, at each wingtip, there is a fuel jettison control valve. Normally that's closed. Matter of fact, it's safety wired in the dump panel. Now, there's only 3 ways you can get fuel from the tanks into this jettison manifold. That's from tank number 2, tank number 3, or the center tank. It's the only way you're going to get fuel from the aircraft into the jettison manifold. And that's done by 2 pumps connected together and comes into this manifold. These pumps are not the pumps that are used to pump fuel to the engines. There's a check valve function in here, so fuel can only come out, fuel cannot go in. And we have 2 pumps over here coming in here. And, of course, we can jettison fuel from the center tank into the jettison manifold, and that is done by an additional line that's here that has a shut-off valve. Now, the 2 pumps here, the 2 pumps here, and the 2 pumps controlled by the switches here for the center tank are much higher pressure pumps. They're about twice the pressure of the normal pumps for the fuel boost pump system. So they will override the fuel boost pump system whenever they're turned on. Now, how is this useful to us? Well, when you want to dump fuel, you can dump fuel from these 3 tanks, and roughly the dump fuel, the dump rate is approximately 1,000 pounds per pump. So if all 6 pumps are operating, you're dumping at a rate approximately 6,000 pounds a minute. If you don't have any center tank fuel, just these 4 pumps are operating, and the rate is closer to 4,000 pounds a minute. Now, the general rate that is normally given is 5,000 pounds a minute, and that's an average of the total operation on these pumps. This can also be used to take care of a failed crossfeed or a boost pump failure where 2 boost pumps fail in 1 inboard tank. Now let me show you how this happens. If the boost pumps, say from tank number 3, both boost pumps fail, fuel can be taken through the dump system by turning the jettison dump manifold system on, putting fuel into this line, and bringing fuel around in through the number 3 open crossfeed to the engine. The only limitation to this is the undumpable value of these pumps, which are around 8,000 pounds. Up to that point, you can manage the fuel very nicely by using the jettison override. However, if you do that, you have to be careful of the arrangement of the other crossfeed systems, because if you leave, for example, this one on, it will also feed fuel to that tank. In other words, once you put fuel from the dump manifold system into the crossfeed manifold system, it will override any pump that you leave a crossfeed valve open to. Okay, now let's relate these controls we just talked about to the dump panel. The two bottom jettison nozzle valve switches are the ones that are at the very end. The top row switches are for the pumps that are in the tank on tanks 2 and 3. The jettison valve center wing, left and right, are the two valves right here. Now there's no check valve in there. Fuel can flow from the crossfeed into this way or from this way into the crossfeed. Normally it's used to go into the crossfeed. The two valves I did not talk about are the number 1 and the number 4 transfer valves. They are very similar to the reserve valves, and they are gravity flow. They allow fuel to gravity flow from the outboard main to the inboard main by opening the valve. And that's about as sophisticated as you can make the fuel dump system. Right there. Okay, coming back to the fuel panel itself, a couple things we should make note of is we have little arrowheads right here, and those are supposed to represent check valves. The reason for the check valve is if one pump is overriding another, it could pump fuel right back into the tank rather than to the engine, and you'll lose pressure of fuel coming to the engine. Normally on the flight engineer's pre-flight, these switches would be turned on one at a time. For example, you turn on the forward number 1 pump, you see the number 1 pump light goes out and the number 2 pump light stays on. If the number 2 pump light goes out, that would indicate a leaking or seeping check valve. Now that system breaks down when we talk about the number 2 system with the APU running. The aft pump on the APU is overridden. Even with the switch off, the light will be out and the pump will be operating anytime ground power or aircraft power is available to operate the pump for the APU with the APU start switch in the on position. So if you're going to check the number 2 pump aft, that would have to be done prior to starting the APU. All blue lights here are in transit lights. When you operate a reserve valve or crossfeed valve, the blue light should come on for a few seconds and go out. If the light comes on and stays on, that means the valve was in the last position or stuck somewhere in transit. You can tell whether it's stuck somewhere in transit or in the last position by reversing the movement of the control switch to the other position. The light immediately goes out, then it was stuck in the opposite position. If the light stays on, it's stuck somewhere in transit. We have 4 fuel shutoff valves. These valves are normally open. When they close, the light goes bright. When they reach the full close position, the light goes dim. On some operators' aircraft, the light is operated and the valve is operated through the fuel start lever on the console. On other aircraft, the light is out all the time, indicating the valve is open, and it is operated only by the guarded switch being moved to the closed position or the fire switch being pulled. Either one will operate that valve. Fuel heat switches operate off of pneumatic air from the engine. If the engine shut down, fuel heat isn't going to work. If fuel heat switch is left on prior to engine start, you're going to bleed air off that engine. You may get a hung or a hot start. The fuel heat provides heat to the fuel filter, which is between the first and second stage engine-driven pump. If excessive pressure or ice is causing that filter bypass, you'll get an icing light. An icing light would indicate the need for fuel heat. However, if the fuel temperature is above freezing, the icing light may indicate contaminated fuel. We have a selector push button here with a temperature gauge. The tank temperature looks at tank number 1. And the outboard main tanks are generally colder than the inboard, and will give you an indication of what the actual temperature is in that tank. If you push any one of the other 4, it will indicate the temperature at the fuel filter. And it will also indicate the temperature buildup of the fuel as fuel heat is being used. For example, if you wanted to put fuel heat on number 1 engine, push selector number 1 and it would register the actual temperature at the filter. When you turn the fuel heat on, the green light will come on indicating pneumatic pressure is available to the fuel heater, and the fuel temperature will go up, and generally it will peg out at plus 60. When you applied the appropriate fuel heat, you turn the fuel heat to close, the green light will go out, and the temperature will drop down to what it was near the value prior to putting on fuel heat. A couple other things that are located on this panel is a fuel use gauge. The fuel use gauge works off the fuel flow indicators on the front instrument panel. If the fuel flow indicator is inoperative, the fuel use gauge will also be inoperative. It works on the fuel used times time. The fuel used times time is burnout. This gauge represents the fuel being used by number 1 engine only. It's downstream of the fuel shutoff. There may be a discrepancy between the fuel load and what was used out of the fuel load and the fuel used. And that discrepancy would be the fuel that's used by the APU. It is not recorded on the fuel used gauges. The fuel for the APU comes from the number 2 main tank with a separate pump, the green DC pump, or the aft main pump, AC main, to supply fuel to the APU. And there's a little arrow here showing the line going to the APU. Now downstream of this line there is another fuel shutoff valve which is operated by the start switch of the APU and or the APU fire switch. We have directly above the center tank a scavenge pump. The problem here being that the 2 jettison override pumps are not located at the lowermost point of the center fuel tank, and they leave several thousand pounds of fuel in the center tank when they stop pumping. So to make advantage of that particular fuel and be able to use it, we can turn the scavenge pump to the on position. The scavenge pump will then pump the fuel that's remaining into the number 2 main tank. And many times this can counterbalance or take up and replace the fuel that was used by the APU to keep the fuel tanks balanced. When the jettison override pump is on, the low pressure light is activated, and if the pump is working, the light goes out. When it runs out of fuel in the center tank, then the light will start blinking at you and eventually be on steady. At that point, the switch should be turned off. When you turn the switch off, the pressure light for the jettison, for the scavenge pump will be deactivated. It is not active when the switch is off. There is a caution on this particular switch that you should be aware. If on a fuel load that requires center tank fuel, generally all the mains are full. And if the number 2 main is full and you turn the scavenge pump to the on position, it will try to put fuel into the full tank. No room. So what happens to it? It'll go through the vent system and come out the wingtip where the fuel tank is vented. So caution must be used for operation of the scavenge pump on the ground when the main tanks are full. Well, that completes the second officer's panel, and now we'll go to the overhead panel, and we'll start in the lower right-hand corner with window heat. Window heat has 4 switches, which in the forward position activates the 2 front windows and the 4 side windows. The front windows, being a double compound curve, is a very sophisticated heating system. The side windows on the left and right side are simply a thermal off-on switch, which is relatively unsophisticated. To indicate whether the window heat is working or not, we have 6 lights here, 1 for each of the windows. When power is going to the window, the light will be illuminated, and when it cycles off, the light will go out. Since the cycling of these lights may be distracting, there's a center button right here called Power Lights, which you can deactivate the operation of the lights. It doesn't affect the operation of the window heat whatsoever, but simply turns the lights out so they don't sit there and flash at you. On turning on window heat, caution should be used if it's very, very cold outside, because of the heat may cause a very thin outer pane to have a thermal shock and possibly crack or break on you. Turning on the window heat when the temperature is below freezing, and some operating manuals it's 20 degrees, the heat should be turned on for 3 minutes and then turned off for 2 minutes and then turned back on and left on the cockpit setup on a pre-flight. And this should allow at least a half an hour for the windows to stabilize temperature prior to takeoff. The buttons on the left and right side of the power lights are associated only with the 2 center switches. If it's a fairly warm day and you turn on the heat and the windows are above its operating cycling temperature, the light won't come on. To assure yourself that the heating system is working, you can hit the button to the left, and that will automatically override the temperature control and turn the main number 1 left and the number 1 right center windows on, and green light will come on. However, if you hold that switch too long, the system could overheat and automatically trip them off. There is a light back on the flight engineer's door panel which would indicate when this happens. If it should happen, you can reset the window by going to the off position and then back on again. To the right, there is an overheat test, which normally is not used. As a matter of fact, we have a guard covering it so you don't accidentally put it on. And anytime you hit that, it trips the number 1 left and the number 1 right window heat off and lights the overheat light. The only way to get this back is to turn the switch back to the off position and back on again. Now, this could lead into a fairly serious trap in flight. If the window heat is turned off in flight and the window allowed to cool and then the window heat turned on again, the chances are much higher than normal to possibly have a windshield shatter on you. So anytime the window heat is turned off or fails in flight, it should be left off for the remainder of the flight. The window heat is not necessary for bird proofing or pressure differential in the airplane. Even if the window shatters, there is no need to depressurize the airplane. The actual window is approximately 3 inches thick, and the part that shatters is less than 1/8 of an inch on the outer pane. It's actually the glass on the outer pane is to make it easier to clean the window without scratching the plastic which makes up the main part of the windshield. Moving up to the probe heaters, this particular aircraft has 6 lights here, and in the center instrument panel there's an additional light that comes on when any one of these 6 lights come on. Some aircraft, instead of having lights here, they have 2 ammeters. The ammeters would, with push buttons, would indicate the actual amps being drawn by each probe heater. On this particular system, when the switches are placed to the on position and the aircraft is on the ground, the total air temperature probe heaters are not activated, but the lights are out. In other words, when the switch is off, all lights are on. When the switch is placed on, which is normally done on taxi, all lights go out. However, the total air temperature probes do not receive any heat. They will receive heat as soon as the airplane is rotated and nose wheel leaves the ground. Now, when the switch is in the on position, if any one of the probe heaters fail, the light will illuminate. And appropriate action would be taken for that particular failure. I might point out that the aux pitot and the main pitot actually has 2 loops of heaters. Either one of the loops will cause the light to come on. So when the light comes on, you don't know whether you have total POP failure or just one loop. Most of the time, most likely it would be just one loop. Moving up to the wing anti-ice, we have a ground test switch. When you move the switch to ground test, you activate the left and right wing anti-ice valves to the open position to check operation. The blue light will come on and then go out to indicate the valve is open. If the switch is held in the ground test position long enough, the wing pneumatic air will cause the wing anti-ice to heat to the point it will cause the valves to close. Normally that should not be done. It only takes a few seconds to go to the ground test. The blue transit lights come on and then go out. You release the switch, the blue and transit lights come on and go out. I might also point out that the air that you're using in the ground test, if it's done during a pre-flight using the APU, will take air away from the packs to operate the wing anti-ice, and the packs may shut down while the wing anti-ice is being tested. When you release the switch, duct pressure comes back up, then the packs will come back in operation. In flight, turning the wing anti-ice to the on position will activate the pneumatic air to those areas directly behind the leading edge flaps. It should be pointed out that the leading edge flaps extended in flight just dumps this high air overboard, and little to no anti-icing takes place, and you're just throwing away bleed air. So the wing anti-ice should not be operated with leading edge flaps extended in flight. Moving up to the nacelle anti-ice, the green lights represent the pneumatic control valves for the anti-ice. Moving the switches to the on position with the engine shut down, the valves can't operate. However, if you leave the switch in the on position with the engine shut down and then subsequently try to start the engine, bleed air will be bled off of that engine, and possibility of a hot or hung start could occur. So these switches should be checked to make sure they're off prior to engine start. If icing conditions exist, the nacelle anti-ice should be turned on as soon as practical after engine start, probably before taxi. And the reason being, with the engine running, the acceleration of air coming into the engine could cause ice to form on the inside of the nacelle. And if you taxi a considerable period of time and then turn them on, the taxi idle RPM of the engine may not be sufficient to melt off the ice. However, when you apply takeoff thrust, that will melt off the ice and maybe cause the engine to flame out during the takeoff roll. It's not uncommon when you turn on the nacelle anti-ice to have the nacelle light stay out. At idle RPM, not enough pressure is available to operate the valve to the full open position. You may be getting a slight amount of anti-ice, but not enough to cause nacelle icing to occur. If this is the actual condition and you have an extended taxi time, clearing the engines by running the throttles up prior to takeoff for a period of time to make sure the nacelle anti-ice applies enough heat to cause the anti-ice system to do the job. Moving up to the stall warning. Stall warning power off light is normally on during the cockpit setup. The light could indicate one of two things. It could indicate there's no power to the stall warning computer, or it could indicate that the heating element to the stall warning vane is deactivated. Normally with ground power or aircraft or external power being applied to the airplane, the power off light will be on, indicating the stall warning vane is not heated. As soon as aircraft power is supplying the aircraft buses, the power off light should go out, indicating the heater is working and the computer has power. If in flight the power off light comes on, it could still indicate either a heater failure or a computer failure. The simplest way to tell is do a little test here, and if it tests, then it's a heater failure. If it doesn't test, the stall warning is inoperative. For maintenance, there is a heater off position that should not be used by the flight crews. It is normally in a normal position, and on a cockpit setup, going to the test will check out the system. When you go to the test position, it will cause three things to happen. It will cause the motor and the stick shaker to operate, and the control column will shake. It will cause the power off light to go out and apply heat to the stall warning vane, and it will cause this little disc here to turn. The little disc is telling you that the inputs from the two sensors that feed the stall warning computer are active. The stall warning computer actually is behind this panel. The two inputs is number one, information from the stall warning vane. Number two, information from the inboard trailing edge flaps, as the position of the flaps will have an effect upon the angle of attack which the stall warning vane will operate off of. One other point I'd like to make about the stall warning system. It has no inputs whatsoever from the pitot-static system, the airspeed, altimeter, or any of that system. This works strictly off of stall warning vane position, which is angle of attack, and flap position. Master radio switches. Normally these switches are on. The only time they're turned off is in case of maybe an electrical fire, somebody spills some coffee on the console or something like that, or on parking on terminating flights. The thing to remember about the master radio switches is the essential switch does not turn off all the items that the number 2 switch does. The exception being the items that are powered by the standby AC and DC buses are not affected by the master radio switches. For example, the VHF nav radio, the number 1 comm, the glide slope. They are not activated by this master radio switches, where they are activated by the master radio switch number 2. Next item I'd like to talk about is the engine fire switches. There's 4 of them. And the engine fire switches and the APU fire switches are constructed exactly the same. They don't come out very far when you pull them, approximately an inch. However, when you do pull them out, a flag behind the fire switch will rotate 90 degrees and block the fire switch from being pushed back in. If, for whatever reason, you want to put the fire switch back in, you're going to have to manually move that flag even with the fire switch to be able to push the handle back in. Now, I'd like to review some of the items that are operated by the fire switch. When you pull the fire switch, effectively what you're doing is you're putting a knot and closing off all the items that are going through the pylon. Most important is to shut off the fuel. Most engine fires, once you get rid of the fuel, the fire will normally stop by itself. We also stop the engine hydraulic fluid from going through there. The hydraulic fluid, of course, is mounted on the engine, and once that gets hot enough, that could provide a source of combustion for the fire. Although it takes a very high temperature to get it going, once it gets going, it burns very hotly. It also trips the aircraft generator and the generator breaker, and closes the pneumatic air control valve. And one additional thing it does, it arms the buttons for discharge of the bottle. Right here, these bottles are not armed until the fire switch is pulled out. Then upon pushing on the button, the bottle will fire the squib, rupture the bottle, and allow the freon to flood the engine, and the light will stay on for as long as the power is on the aircraft. If the fire is severe enough, a second bottle being discharged is available. However, just because the fire light goes out on the fire switch does not necessarily mean the engine fire is out, because there's a strong possibility on a severe fire that the fire detection system could be destroyed. And once it's destroyed, the light will go out, even though the fire is going very strongly. So if there's ever any doubt, after 30 seconds, you would fire the second bottle. Okay. Next thing I'd like to talk about is this flight control panel right here. Normally, these switches are not used by the flight crews. The only exception to that might be the number 4 switches, the upper and lower number 4 switches. This may sometimes be used when pneumatic air isn't available and the only source to pump up the brake pressure is the electric pump. Now, the electric pump is a very low flow pump. It doesn't have much muscle. And if there's a older aircraft or leakage in the power packages, it may not be able to build the pressure up to 3,000 psi. If that's the case, by closing the number 4 system on the upper and lower switches, that cuts off all flow going to the flight controls, and then the electric pump can build up to 3,000 psi. This should not be done at any other time except during the pre-flight on the ground. The thing I might point out here is the 4 upper switches are associated with the hydraulic flight controls that are located in the empennage, or tail of the aircraft. The 4 lower control switches are associated with the items that are controlled in the wing. Physically, the shutoff valves are 4 in the tail and 4 in the aft spar of the wing. Let's take an example here. When we close or open system number 1 switch on the upper panel, you will deactivate everything in the tail that is located on this panel that says number 1. And specifically, one of the actuators to the upper rudder, the left outboard elevator, and the right inboard elevator. That's all. This is also useful information if you should have a hydraulic system 1 failure. You can look on this panel and see the items that will be deactivated by that hydraulic system failure. Normally you wouldn't activate the switches, but the panel is for example, System 1 hydraulic failure would deactivate the left outboard elevator and remove one actuator from the upper rudder. Remove one actuator from the right inboard elevator. The rudder and the inboard elevator would operate normally. The outboard left elevator would not operate at all. So effectively, the only thing that's going to affect on System 1 failure would be the outboard elevator. Taking the lower panel, using the same example, everything here labeled 1 will have no hydraulic pressure to it. It would be a CCA, which is the control actuator, central control actuator, which is essentially a power boost to the roll control of the airplane. One actuator would be inoperative here. On the inboard aileron, one actuator would be inoperative, and the outboard aileron, one actuator would be inoperative. In no case would it deactivate anything in this system at all. Another thing to point out here is you have a schematic here showing all the spoilers that are activated by the hydraulic systems. And spoilers get hydraulic pressure only from systems 2, 3, and 4. There are no spoilers that are activated by System 1. Coming down one more panel, we have the yaw damper controls. And there is a test switch here for the turn controller and the yaw damper, which can be activated while you're on the ground. However, they're deactivated in flight. One of the problems associated with this test is not very complete, and an actual yaw damper test would be better conducted by watching your flight control indices while you're taxiing on the ground. This switch right here is called standby ignition switch. In the normal position, it's deactivated. It is a very, very important switch in the aircraft. Its primary function was put in the airplane to relight the engine in case of 4-engine flameout. In most early jets, the ignition system was DC, and that could be backed up by the aircraft battery. On the 747, we have a low-power continuous ignition system, and it is activated by AC. Now, if something should happen, for example, flying through a volcano and having all 4 engines flame out, you lose all AC generators. The only thing left you have is DC. The battery isn't any good to start the engine if it requires an AC ignition system. What this switch does is get AC power off the standby inverter and activate 1 or number 2 igniter. It's the same igniters that you normally use with your ignition switches here. Only the source of power has been changed from the normal AC buses to standby AC. On the flight engineer's panel, the standby green light has to be illuminated for this to work. One other thing it does, which is a little tricky, is it deactivates the captain's compass system. The reason for that is the standby inverter was made to carry just certain items, and when you put the ignition on it, it overloads the inverter, so they had to get rid of something, and they decided the captain's compass system was the most expendable, and that is deactivated. So anytime the standby ignition switch is out of the normal position, the number 1 compass system will be inoperative, and the captain's HSI heading flag will be displayed. Also, this will deactivate the first officer's RMI. Emergency exit lights. As in other aircraft located throughout the airplane, there are lights that are intended to help the passengers evacuate the airplane in case of an accident where power is lost to the aircraft. In the arm position, it takes loss